X-ray astronomy is an observational branch of astronomy which deals with the study of X-ray observation and detection from astronomical objects. X-radiation is absorbed by the Earth's atmosphere, so instruments to detect X-rays must be taken to high altitude by balloons, sounding rockets, and satellites. X-ray astronomy is the space science related to a type of space telescope that can see farther than standard light absorption telescopes, such as the Mauna Kea observatories, via X-ray radiation. X-ray emission is expected from astronomical objects that contain extremely hot gases at temperatures from about 1,000,000 Kelvin to hundreds of millions of Kelvin. Although X-rays have been observed emanating from the Sun since the 1940s, the discovery in 1962 of the first cosmic X-ray source was a surprise. This source is called Scorpius X1, the first X-ray source found in the constellation Scorpius. The X-ray emission of Scorpius X1 is 10,000 times greater than its visual emission, whereas that of the Sun is about 1,000,000 times less. In addition, the energy output in X-rays is 100,000 times greater than the total emission of the Sun in all wavelengths. It is now known that such X-ray sources as SCO X1 are compact stars, such as neutron stars or black holes. Material falling into a black hole may emit X-rays, but the black hole itself does not. The energy source for the X-ray emission is gravity. Infalling gas and dust is heated by the strong gravitational fields of these and other celestial objects. Many thousands of X-ray sources are known. In addition, the space between galaxies and galaxy clusters is filled with a very hot, but very dilute gas at a temperature between 10 and 100 megakelvins. The total amount of hot gas is 5 to 10 times the total mass in the visible galaxies. Sounding rocket flights. The first sounding rocket flights for X-ray research were accomplished at the White Sands Missile Range in New Mexico with a V-2 rocket on January 28, 1949. A detector was placed in the nose cone section, and the rocket was launched in a suborbital flight to an altitude just above the atmosphere. X-rays from the Sun were detected by the U.S. Naval Research Laboratory Blossom experiment on board. An Aero B-150 rocket was launched on June 12, 1962, and it detected the first X-rays from other celestial sources. The largest drawback to rocket flights is their very short duration and their limited field of view. A rocket launched from the United States will not be able to see sources in the southern sky. A rocket launched from Australia will not be able to see sources in the northern sky. X-ray quantum calorimeter project in astronomy. The interstellar medium is the gas and cosmic dust that pervade interstellar space. The matter that exists between the star systems within a galaxy. It fills interstellar space and blends smoothly into the surrounding intergalactic medium. The interstellar medium consists of an extremely dilute mixture of ions, atoms, molecules, larger dust grains, cosmic rays, and magnetic fields. The energy that occupies the same volume, in the form of electromagnetic radiation, is the interstellar radiation field. Of interest is the hot ionized medium consisting of a coronal cloud ejection from star surfaces at 106 to 107 K which emits X-rays. The ISM is turbulent and full of structure on all spatial scales. Stars are born deep inside large complexes of molecular clouds, typically a few parsecs in size. During their lives and deaths, stars interact physically with the ISM. Stellar winds from young clusters of stars and shock waves created by supernovae inject enormous amounts of energy into their surroundings, which leads to hypersonic turbulence. The resultant structures are stellar wind bubbles and superbubbles of hot gas. The Sun is currently traveling through the local interstellar cloud, a denser region in the low-density local bubble. To measure the spectrum of the diffuse X-ray emission from the interstellar medium over the energy range 0.07 to 1 keV, NASA launched a Black Brant 9 from White Sands Missile Range, New Mexico on May 1, 2008. The principal investigator for the mission is Dr. Dan McCammon of the University of Wisconsin. Balloons. Unlike a rocket where data are collected during a brief few minutes, balloons are able to stay aloft for much longer. However, even at such altitudes, much of the X-ray spectrum is still absorbed. X-rays with energies less than 35 keV cannot reach balloons. On July 21, 1964, the Crab Nebula supernova remnant was discovered to be a hard X-ray source by a scintillation counter flown on a balloon launched from Palestine, Texas, USA. This was likely the first balloon-based detection of X-rays from a discrete cosmic X-ray source. High-energy focusing telescope. The high-energy focusing telescope is a balloon-borne experiment to image astrophysical sources in the hard X-ray band. Its maiden flight took place in May 2005 from Fort Sumner, New Mexico, USA. The angular resolution of Heft is ~1.5, rather than using a grazing angle X-ray telescope. Heft makes use of a novel tungsten-silicon multi-layer coatings to extend the reflectivity of nested grazing incidence mirrors beyond 10 keV. Heft has an energy resolution of 1.0 keV, full width at half, maximum at 60 keV. Heft was launched for a 25-hour balloon flight in May 2005. The instrument performed within specification and observed Tau X1, the Crab Nebula, high-resolution gamma-ray and hard X-ray spectrometer. A balloon-borne experiments called the high-resolution gamma-ray and hard X-ray spectrometer made observed in X-ray and gamma rays. It was launched from McMurdo Station, Antarctica in December 1991. Steady winds carried the balloon on a circumpolar flight lasting about 2 weeks. Rockoons. The Rockoon was a solid-fuel rocket that, rather than being immediately lit while on the ground, was first carried into the upper atmosphere by a gas-filled balloon. Then, once separated from the balloon at its maximum height, the rocket was automatically ignited. This achieved a higher altitude, since the rocket did not have to move through the lower, thicker air layers that would have required much more chemical fuel. The original concept of Rockoons was developed by CMDR, Lee Lewis, CMDR, G. Halverson, F. Singer, and James A. Van Allen during the Aerobee rocket firing cruise of the US Norton Sound on March 1, 1949. From July 17 to July 27, 1956, the Naval Research Laboratory shipboard launched 8 Deacon Rockoons for solar ultraviolet and X-ray observations at ~30 degrees north to 121.6 degrees west, southwest of San Clemente Island, apogee, 120 kilometers. X-ray astronomy satellites. X-ray astronomy satellites study X-ray emissions from celestial objects. Satellites, which can detect and transmit data about the X-ray emissions, are deployed as part of a branch of space science known as X-ray astronomy. Satellites are needed because X-radiation is absorbed by the Earth's atmosphere, so instruments to detect X-rays must be taken to high altitude by balloons, sounding rockets, and satellites. X-ray telescopes and mirrors. X-ray telescopes have varying directionality or imaging ability based on glancing angle reflection rather than refraction or large deviation reflection. This limits them to much narrower fields of view than visible or UV telescopes. The mirrors can be made of ceramic or metal foil. The first X-ray telescope in astronomy was used to observe the Sun. The first X-ray picture of the Sun was taken in 1963 by a rocket-borne telescope. On April 19, 1960, the very first X-ray image of the Sun was taken using a pinhole camera on an Aerobee high rocket. The utilization of X-ray mirrors for extrasolar X-ray astronomy simultaneously requires the ability to determine the location at the arrival of an X-ray photon in 2 dimensions and a reasonable detection efficiency. X-ray astronomy detectors. X-ray astronomy detectors have been designed and configured primarily for energy and occasionally for wavelength detection using a variety of techniques usually limited to the technology of the time. X-ray detectors collect individual X-rays and count the number of photons collected, the energy of the photons collected, wavelength, or how fast the photons are detected, to tell us about the object that is emitting them. Celestial X-ray sources. The celestial sphere has been divided into 88 constellations. The International Astronomical Union constellations are areas of the sky. Each of these contains remarkable X-ray sources. Some of them have been identified from astrophysical modeling to be galaxies or black holes at the centers of galaxies. Some are pulsars. As with sources already successfully modeled by X-ray astrophysics, striving to understand the generation of X-rays by the apparent source helps to understand the Sun, the universe as a whole, and how these affect us on Earth. Constellations are an astronomical device for handling observation and precision independent of current physical theory or interpretation. Astronomy has been around for a long time. Physical theory changes with time. With respect to celestial X-ray sources, X-ray astrophysics tends to focus on the physical reason for X-ray brightness, whereas X-ray astronomy tends to focus on their classification, order of discovery, variability, resolvability, and their relationship with nearby sources in other constellations. Within the constellations Orion and Eridanus and stretching across them is a soft X-ray hotspot, known as the Orion-Eridanus superbubble. The Eridanus soft X-ray enhancement, or simply the Eridanus bubble, a 25 degrees area of interlocking arcs of H-alpha emitting filaments. Soft X-rays are emitted by hot gas in the interior of the superbubble. This bright object forms the background for the shadow of a filament of gas and dust. Here the filament absorbs soft X-rays between 100 and 300 electron volts, indicating that the hot gas is located behind the filament. This filament may be part of a shell of neutral gas that surrounds the hot bubble. Its interior is energized by ultraviolet light and stellar winds from hot stars in the Orion OB1 association. These stars energize a superbubble about 1200 lis across, which is observed in the visual and X-ray portions of the spectrum. Proposed X-ray observatory satellites. There are several projects that are proposed for X-ray observatory satellites. See main article link above. Explorational X-ray astronomy. Usually observational astronomy is considered to occur on Earth's surface. The idea of limiting observation to Earth includes orbiting the Earth. As soon as the observer leaves the cozy confines of Earth, the observer becomes a deep space explorer. Except for Explorer 1 and Explorer 3 and the earlier satellites in the series. Usually if a probe is going to be a deep space explorer, it leaves the Earth or an orbit around the Earth. For a satellite or space probe to qualify as a deep space X-ray astronomer's explorer or astronobot explorer, all it needs to carry aboard is an XRT or X-ray detector and leave Earth orbit. Ulysses is launched October 6, 1990, and reached Jupiter for its gravitational slingshot in February 1992. It passed the South Solar Pole in June 1994 and crossed the ecliptic equator in February 1995. The Solar X-ray and Cosmic Gamma-ray Burst experiment had three main objectives: study and monitor solar flares, detect and localize cosmic gamma-ray bursts, and in situ detection of Jovian aurora. Ulysses was the first satellite carrying a gamma burst detector which went outside the orbit of Mars. The hard X-ray detectors operated in the range 15 to 150 keV. The detectors consisted of 23 mm thick times 51 mm diameter CSI crystals mounted via plastic light tubes to photomultipliers. The hard detector changed its operating mode depending on measured count rate, ground command, or change in spacecraft telemetry mode. The trigger level was generally set for 8 sigma above background and the sensitivity is 10⁻⁶ erg per square centimeter. When a burst trigger is recorded, the instrument switches to record high-resolution data, recording it to a 32 kbit memory for a slow telemetry readout. Burst data consist of either 16s of 8 ms resolution count rates or 64s of 32 ms count rates from the sum of the two detectors. There were also 16-channel energy spectra from the sum of the two detectors. During wait mode, the data were taken either in 0.25 or 0.5s integrations and 4 energy channels. Again, the outputs of the two detectors were summed. The Ulysses soft X-ray detectors consisted of 2.5-mm thick times 0.5 square centimeters area sea surface barrier detectors. A 100 mg per square centimeter beryllium foil front window rejected the low-energy X-rays and defined a conical FOV of 75 degrees. These detectors were passively cooled and operate in the temperature range -35 to -55 degrees Celsius. This detector had 6 energy channels, covering the range 5 to 20 keV. Theoretical X-ray astronomy. Theoretical X-ray astronomy is a branch of theoretical astronomy that deals with the theoretical astrophysics and theoretical astrochemistry of X-ray generation, emission, and detection as applied to astronomical objects. Like theoretical astrophysics, theoretical X-ray astronomy uses a wide variety of tools which include analytical models to approximate the behavior of a possible X-ray source and computational numerical simulations to approximate the observational data. Once potential observational consequences are available, they can be compared with experimental observations. Observers can look for data that refutes a model or helps in choosing between several alternate or conflicting models. Theorists also try to generate or modify models to take into account new data. In the case of an inconsistency, the general tendency is to try to make minimal modifications to the model to fit the data. In some cases, a large amount of inconsistent data over time may lead to total abandonment of a model. Most of the topics in astrophysics, astrochemistry, astrometry, and other fields that are branches of astronomy studied by theoreticians involve X-rays and X-ray sources. Many of the beginnings for a theory can be found in an Earth-based laboratory where an X-ray source is built and studied. Dynamos. Dynamo theory describes the process through which a rotating, convecting, and electrically conducting fluid acts to maintain a magnetic field. This theory is used to explain the presence of anomalously long-lived magnetic fields in astrophysical bodies. If some of the stellar magnetic fields are really induced by dynamos, then field strength might be associated with rotation rate. Astronomical models from the observed X-ray spectrum, combined with spectral emission results for other wavelength ranges. An astronomical model addressing the likely source of X-ray emission can be constructed. For example, with Scorpius X1 the X-ray spectrum steeply drops off as X-ray energy increases up to 20 keV, which is likely for a thermal plasma mechanism. In addition, there is no radio emission, and the visible continuum is roughly what would be expected from a hot plasma fitting the observed X-ray flux. The plasma could be a coronal cloud of a central object or a transient plasma, where the energy source is unknown, but could be related to the idea of a close binary. In the Crab Nebula X-ray spectrum there are 3 features that differ greatly from Scorpius X1. Its spectrum is much harder, its source diameter is in light years s, not astronomical units, and its radio and optical synchrotron emission are strong. Its overall X-ray luminosity rivals the optical emission and could be that of a non-thermal plasma. However, the Crab Nebula appears as an X-ray source that is a central freely expanding ball of dilute plasma, where the energy content is 100 times the total energy content of the large visible and radio portion, obtained from the unknown source. The dividing line, as giant stars evolve to become red giants, also coincides with the wind and coronal dividing lines. To explain the drop in X-ray emission across these dividing lines, a number of models have been proposed. Low transition region densities, leading to low emission in coronae. High density wind extinction of coronal emission. Only cool coronal loops become stable. Changes in a magnetic field structure to that an open topology, leading to a decrease of magnetically confined plasma, or changes in the magnetic dynamo character, leading to the disappearance of stellar fields, leaving only small-scale, turbulence-generated fields among red giants. Analytical X-ray astronomy. Analytical X-ray astronomy is applied to an astronomy puzzle in an attempt to provide an acceptable solution. Consider the following puzzle. High-mass X-ray binaries are composed of supergiant companion stars and compact objects, usually neutron stars or black holes. Supergiant X-ray binaries are HMXBs in which the compact objects orbit massive companions with orbital periods of a few days, and in circular orbits. SGXBs show typical the hard X-ray spectra of accreting pulsars and most show strong absorption as obscured HMXBs. X-ray luminosity increases up to 1036 erg-1. The mechanism triggering the different temporal behavior observed between the classical SGXBs and the recently discovered supergiant fast X-ray transients S is still debated. Aim: use the discovery of long orbits to help discriminate between emission models and perhaps bring constraints on the models. Method: analyze archival data on various SGXBs such as has been obtained by integral for candidates exhibiting long orbits. Build short and long-term light curves. Perform a timing analysis in order to study the temporal behavior of each candidate on different timescales. Compare various astronomical models. Direct spherical accretion. Roche lobe overflow via an accretion disk on the compact object. Draw some conclusions. For example, the SGXB SAX J1818.6-1703 was discovered by Beppo-Sachs in 1998, identified as a SGXB of spectral type between 09I-B1I, which also displayed short and bright flares and an unusually very low quiescent level, leading to its classification as a SFXT. The analysis indicated an unusually long orbital period, 30.0 plus or minus 0.2 d in an elapsed accretion phase of ~60, implying an elliptical orbit and possible supergiant spectral type between BO 5 to 1I with eccentricities E~0.3 minus 0.4. The large variations in the X-ray flux can be explained through accretion of macro clumps formed within the stellar wind. Choose which model seems to work best. For SAX J1818.6-1703, the analysis best fits the model that predicts SFXTs behave as SGXBs with different orbital parameters, hence different temporal behavior.